Hello, beloved sibling. You know, Peggy, I predict that this is going to be a really great. This is my what was it, Johnny Carson character? You remember that? I predict that this is going to be a really fascinating show. But anyway,
You predict? Really? You predict?
I predict. Yes, I can
How
predict.
often do you predict, Aaron?
Well, let me just say, you probably possibly you may not understand the deep neuroscience investment here, but it's actually been known for a long time that one of the primary fundamental functions of the human brain is to predict the future. Are you shocked?
Why is that?
Why is that? Because, well, obviously there is an evolutionary advantage to the ape who can.
What? Hey, Aaron, what if I want to live in the present? What's wrong with that? Why can't I live in the present?
Well, I actually do know the answer to that question, but because you're Peggy Mason, you should explain it to us.
No. Let's hear you explain why I can't live.
The reason you can't live in the present is because you can't see the present, all of the present. All you get to do is see what happened a few milliseconds ago. That's it. You don't get to. When I'm looking at you, even if there's not a delay in the video signal, even if there's no delay in the video signal, if I'm standing right in your home, I'm only seeing the you several milliseconds ago. Just as we all know,
even more tens of milliseconds to hundreds of milliseconds ago.
But just as we all know that when we look at the sun, we're seeing light that left the sun 11 minutes ago. And this is old news.
So the astronomers figured this out maybe a little bit before the neuroscientists, but we've caught up. And now we know that the brain is a predictive machine. That's what it's built to do. And it has to, because it really has to figure out, by the time I go to do something, the world has changed from what it was when I started my movement.
Right. And, and again, but what we're going to talk about here is this new research about how effective brains are, how, in my view, astonishingly effective brains are in predicting the next word that you will say, which is a phenomenon that I have, up until recently, really only associated with people who had been married for a long time. This joke about what? I'm just saying, this joke about finishing each other's sentences. This is an old joke, an old phenomenon. Like for example, Luana Anderson. When I see her at the Neuroscience 2018, I'm sure that I will be able to predict what she's going to. No, I won't be able to predict what she'll say because she'll say it in Spanish.
No, she can talk to you in English.
Well, that's true too. She will deign to talk to us in English.
Yes.
But again, I've always thought of this as just a thing that happened with familiarity. But the research tells us that it's not something that we're not merely able to predict those with whom we are familiar, the patterns, speech patterns of people with whom we are intimately familiar.
Yeah, I remember that we've talked a lot about making shortcuts to do things faster. So one of the faster ways that you can do things is to decide that what you're going to do is you're going to expect what you're going to see, because it's a situation that you've seen a million times before. You're not really going to pay attention. You're not going to process the incoming sensory input. You're just going to say, oh, I expect this. And unless something, some foghorn tells you, no, it's not the same, it's different, then you're going to say, oh, well, every other time I've been in this situation, I've heard, open your notebooks, please. And so now I open my notebook.
Well, you and I have talked about this a little in some detail in our video about baseball.
Right.
And how batters have a quarter of a second between the time the ball leaves the pitcher's hand and arrives in the catcher's mitt. And during that time, my mind was blown then at the sophistication of the calculation that just normal brains have.
Well, I just want to get it out of the baseball players' domain and remark that we all have this ability. And this is an old result that I always have loved this result. It was an Australian neuroscientist. I think her name is Pam Davis. but what she found, and I think this has been confirmed or repeated, is that the breath that you take in before you speak a sentence is approximately the right length so that you can say all the words that you have to say, which means that before you take the breath, you already know what you're going to say. You think you're just talking, blah, 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 blah. But already your brain knows about how long the sentence is that you're going to say. And that's really amazing.
Well, no, but there's also a, let me grab myself right here. There's also a, one of the really interesting, this also works with the motor cortex. There's that very famous experiment where they would tell people, press the button when they're on the fMRI, and they say, press the button whenever you feel like it. And there's activation in the motor cortex before you are consciously aware that now you're going to start pressing the button.
Yeah, that's a really famous experiment by Benjamin Libet. And yeah, it's a really, really famous experiment. Somehow I like the example of I'm taking a long breath to say something really long versus I'm taking a short breath to say something short, because first of all, we all do it. And second of all, taking a breath before you talk, that's essentially ancient history in neurological terms. It's seconds. It's time enough for you to go around and around the nervous system about 500 times, across 1,000 synapses. So it's really an amazing effect. And kids do it, and you do it, and I do it. Everyone does it. And, we got all this whole thing, this wonderful thing that we call the brain for free.
But so in this recent study, which was published in Nature, and based on research that was done in the Basque region of Spain, which I don't speak any Basque. I wonder if the Luani.
Well, they did it in Spanish. I don't know what the politics of that is, but they did it in actual Spanish.
Well, that's a good point. Of course, but thanks to good old Google Translate, we were able to read it. I was able to read it.
No. They presented in English, but yeah. So it's a really interesting expectation that they found that we have, that I didn't know that I expected.
Well, so tell us what it is that the brand new news here about what our brains do.
It turns out there are different classes of consonants. There are fricative sounds, and fricative sounds means that the air is going through a small opening. And then there are what are called plosive. Do not put an EX there, just plosive. Okay? Plosive sounds. And plosive sounds are sounds that go, stop. So they're stopping. And
for example,
the voiceless plosive sounds are p, t, k. And then the fricative sounds are fa, tha, sa. You can see that's sort of more intuitive to me. Fa, you can see that it's going through a little hole. Tha, sa.
Right.
So what turns out is that they showed people pictures. So a picture of a sandal, and then they say the word sandal. And there were a picture of a cannon, and then they say the word cannon.
These were pictures, people who were hooked up to a weird machine that I never heard, an MEG machine.
It's called a magnetoencephalography machine. And so it's akin to an EEG, an electroencephalography, but it uses a magnetic field instead of electrical field. It has slightly different properties, but the basic idea is the same. You're basically getting a measure of
a live
automated activity in the brain.
All right, so they're sitting under this machine, and we're getting a live readout of some of the things that are the activity in their brains, and they're being shown a picture and then having a word associated with it.
And what they found was that the people had a different pattern of activation if they were expecting a fricative, a word that began with a fricative consonant versus a word that began with a plosive consonant. So what's sort of surprising to me is, I really was unaware that I was categorizing sounds into fricatives and plosives until I looked it up on Wikipedia. I didn't know what they were until I looked it up. So that's that's sort of interesting. But I guess to me it makes some sense because I'm much more likely to mistake a fa for a tha or a fa for a sa than a fa for a, say, pa.
Yeah. Now, so Luani wants to know about whether or not this is a phenomenon that is more likely, I guess, to occur in twins. But this
is not actually the ability to continue in other sentences. Right. I mean, yeah, of course, that is something that we're good at, is to continue the sentences of people or the thoughts of people that we know well. But this is, you're expecting something. You walk into the classroom and you're expecting the person to say good morning, not to say, file your taxes. I don't know.
Yeah.
So you're just expecting the thing that is right for that context.
And the consonants.
And the consonants involved are expected. That's what they're telling us now. And it's expected in the superior temporal gyrus, which is, where the primary auditory cortex is.
Well, yeah, that's another thing. This is an auditory phenomenon. That there's activity in the auditory cortex, which is another, I guess it's not shocking, but just that the auditory cortex is where we find the anticipation, where we find activity.
So another way to think about this is to say that we don't really know. One of the things we don't know at all is, well, not at all, but we don't know it well, how the auditory cortex is organized. So, for example, we know how the visual cortex is organized. We have a really good idea of how the visual cortex. We have a decent idea of how the somatosensory cortex is organized, and we have a controversial but some good guesses as to how the motor cortex is organized. But for the auditory cortex, it's been much more difficult to figure out what are the organizational principles. There is a tonotopy, but what else is going on? And so this is suggesting to me that, there's this fricative versus plosive, blah, 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 blah.
I guess I don't quite get this, because you, my beloved friend, have taken apart more brains than probably anyone I know, have ever known.
Well, taking apart a brain does not tell you how a cortex is organized physiologically.
You can see why this is a bit surprising, because you can take it apart, you've taken it apart slice by slice and every which way. But
yeah, but that doesn't tell you how it's organized.
Apparently not.
You cannot take apart the visual cortex and say, oh, I know that there are orientation selective cells, or there are blobs where there are cells that like certain colors, that respond to different colors. So no, you cannot tell function from just anatomy. Don't get me wrong, I love anatomy.
Yes,
and it's great, but it does not in and of itself. You have to use these various tools together. So you can't take it apart and know how it's organized. So we don't really understand too well how the auditory cortex is organized.
And so this, again, what was unique about this work was that using the help of this
encephalography,
we were able to see where the consonants, what areas of the auditory cortex were responding to consonants as yet unspoken.
Yeah, and consonants in two different classes differently. So they would respond the same to fa, tha, sa, and different from how they would respond to pa, ta, ka.
Oh, by the way, so of course, Loani remembers this because she also was a student of understanding the brain, the neurobiology of everyday life. By the way, I do want to say that we do have the Chicago Brain Buddies podcast, and this particular chat will be on there in a couple of hours after we finish this. So if you'd like to catch up on the chat without actually having to look at us while you're in the car, which we recommend. If you'd like to do it while you're in the car, don't do it. Watch on YouTube. But
you can wait till my next haircut to look at us.
That's right. That's right.
And your next haircut. I mean, man, what's going on there, Aaron? What's going on with the haircut?
You know, I let it go, and it started to look too much like yours, and I was worried to have trouble distinguishing between you and me. And I said, better just to shave it. Okay. So now, but in addition to being really fascinating, this business about the brain being able to tell consonants before they are spoken has some theoretically practical therapeutic value?
I don't know about that. What do you think?
In one of the articles that I read about it, it said that it could be useful for people with autism who have difficulty assessing their environment such that they can respond properly to it. And also that it might be useful for folks who suffer dyslexia. The better we understand it, the better we understand the way the auditory cortex processes information, the more effective we might be in treating some of those disorders.
Yeah. Francesca is asking whether it's just the auditory cortex that has this predictive ability or this foreseeing ability. And no, the answer is, so remember the experiment. I think we've talked about this a few times. Let's say I take a chunk of cortex. Okay. I take it out of an animal, of a mouse, let's say, and I put it into a dish and I record from lots of different cells. I can visually record from them, so I can record from hundreds of cells. And they make even in the dish, they just make a typical pattern. Okay, so they have a little pattern. They dance in a certain way. You know, after Joe dances, Nancy dances, and then Tom does, and so on. So they're in a little chain. It's a circuit.
You mean like a slice of brain tissue?
What's that?
You mean if you took like a slice of brain tissue? Yeah,
it's a slice of brain tissue, a slice of cortex, and it's going to have a certain circuit that's stereotyped, and it does its little thing. Well, there's a finding that comes from people such as Rafa Yusta and one of my colleagues here, Jason McLean, that shows, and this has been repeated by many others, that the activity that you see just spontaneously there in the cortex is the same activity that you would get if you stimulated the sensory input from thalamus. So in other words, the brain is sitting there doing its expected thing even without any input. Remember, we say what you see, you know, we are not cameras and we are not tape recorders.
Right.
Well, the fact of the matter is, you know, the cortex is just sitting there with its own little private Idaho idea about what is going to happen next. And it does that regardless of whether it has any input.
Well, you know, that is another really interesting thing about these data, which is that not that I think about it a whole lot, but I sort of had a sense always, or sort of it feels intuitively right, that your auditory cortex, your hearing system, is sitting and waiting for something to happen, but that's not apparently the way it works.
Well, it's sitting and expecting what's going to happen given the context. And I think we've all had the experience where you hear something, you have no idea what the person just said. You replay it a few times in your head, and a demonstrable number of seconds later, oh, that's what they said.
Wow.
Right? You can figure it out. And so what that is it highlights how difficult it is to decode auditory sounds. It's really, really hard to tell even where one word begins and one word ends. And you can figure this out if you listen to a foreign language. If you listen to people talking in a language you don't understand, you have no idea where the space, the silences between the words are, and that's because there are no silences. But there are also no silences in English. But we hear the silences. We hear gaps. and there are no gaps. So we're just making stuff up all the time. We're just predicting.
I don't get it. There's no gaps in English. What are you talking about?
No. If I take my phone, okay, hold on.
We're
gonna do a little experiment.
Check us out on Facebook.
Here's a voice memo, okay?
Okay, yes.
Can you see the screen?
Yes.
Okay, so I'm gonna put it on.
Okay. All right, I see.
Here I am talking. Here I am talking. That's how slow I have to go to get spaces between the words.
Oh, wow. That's a good demonstration. That's a good
Can we do it again? The brain, where is it? Can you see it?
Let me get it bigger for you. No, I can't see it. I can't see it.
Oh, because it. Okay. The brain is so cool. Did I just say one word or did I say a bunch of words?
You obviously said a bunch of words, but it didn't look like there was any spaces in it at all. Just like what I'm talking right now, it doesn't look like there are any spaces in what I'm talking. But it's obvious to you and me and all the folks listening that I am taking spaces.
The brain is so cool. That's what you have to do.
Well, let's just say The Brain is So Cool is also the name of Peggy's wonderful blog, thebrainissocool.com. But okay, wait, but just explain this to me. I don't get it. How in the world, why does it sound like we're taking spaces, but it doesn't?
I have told you, Aaron, we are not cameras and we are not tape recorders. We are interpreters. We are such fantastic interpreters.
It doesn't sound like that. It doesn't sound like that. It goes contrary to everything I know. I mean, I hate that.
Love it.
Well, okay, all right.
So let's see what Francesca, as far as you know, there are studies about these patterns our brains make, like similarity between different species. Bigger patterns are made similar or fractal. Yeah, I don't know how it varies between species. This is probably true in all the various different species. And John, hi John. So if you're speaking with someone whose first language isn't English, would it be more helpful to put in spaces that aren't usually between, as opposed to just speak those words slowly? I mean, I think that is the same thing, that speaking the words slowly. with I don't know. I think when you speak the word slowly, naturally the spaces become more evident. Hi, Allie.
But that is certainly what I think I tend to do with someone who I think is not familiar with English, as familiar as I am. And I certainly know that when I'm listening to a language, I will ask people, please speak more slowly, because I am not able to do it. I'm not able to hear it.
When I'm in Paris, I can understand somebody if they speak slowly. If they speak rapidly, I am so sunk.
Right. And the tendency is, the more familiar you are with a language, the more rapidly you speak, because there's no reason to take that extra time because you're speaking to a fellow native speaker.
Well, yeah, and I think some languages tend to be slower and some languages tend to be faster. So it's a difficult thing if you're trying to learn a language that is fast.
Well, but as Lenny says, that what we are doing when we are speaking more slowly to those for whom English is not first language is putting a separation between. Going slowly is not the same as separating words. Yeah,
I mean, I think that probably slowly is more important, but I also think that the slower you go, the more evident it is where the separations are. But I don't know.
Yes.
I don't know.
We need to get
do an experiment.
Yeah, we need to get Noam Chomsky in here to do this. The real headline here is about the consonants. not so much about the vowels.
Well, the consonants, if I recall correctly, the consonants are the ones are higher frequency. So they're the ones that people miss. So as you start to lose hearing, you're going to lose hearing in the higher frequencies. You're going to start to lose the consonant understanding is going to start to drop out.
Well, and Michael makes a really good point that those of us who are native English speakers, there are versions of English, not only British English, but even Southern English.
Right.
As a matter of fact, just at the personal side, just recently, Sharon was pointing out the fact that I would say, due to my Southern heritage, my mom from Mississippi, my father from Kentucky, I sometimes take one syllable words and make them into two syllable words.
Yeah.
Like in the South, grits is a two syllable word. Grits.
Right.
Whereas people in the North say grits. But
you do it. You do the same thing in Maryland.
Oh, really?
And my brother has much more of a Maryland accent than I do, but in certain moods, I will get very Marylandy, and it'll go. It's almost a Southern drawl.
Well, this may have some treatment, maybe have some clinical applications, according to one of the articles that I read about it. But does it affect it all the way you, as a neurobiologist, does it inform your understanding of the neurobiology of it in any way, to know that the brain, that the auditory cortex has these predictive powers that you didn't know about?
I mean, to me, the most interesting thing is this idea that you separately predict fricatives from plosives, which I just didn't know. I didn't know, because it means I'm categorizing words on an axis that I didn't even know existed. Okay. And, I know that there are a million examples of that. I know that we make judgments all the time that are unconscious judgments using very sharp unconscious boundaries, and I'm not conscious of them. They're unconscious. So I know that, but this is another example of it. And it's a really sort of, to me, it's a really surprising example.
But so
Aaron, you just dropped out for some reason.
I think I'm still here.
Francesca says, I have personal experience about speaking another language. When you ask to go slow, many times people elong their vowels instead of separating them. And they tend to speak loudly. For sure, they speak loudly. What is the book? There's a book about this. One moment. I think the book is Missing Connections. And it talks about the experience of losing your hearing and everyone talking to you much louder, which is completely not helpful. Where in fact what you want is you just missed a couple consonants, and that's what sunk you.
Like our page, Chicago Brain Buddies on Facebook, or check out Chicago Brain Buddies on. You can get on YouTube.
I'm not finding it.
And you can listen to.
I think it's Missing Connections. Anyway, our fearless leader has left us. Our perception and expectation involved in this experiment. I think that the whole thing is about expectation dominating perception. The whole idea here, Luani, is that expectation is what dominates perception rather than actually information. Hi, Aaron. Rather than information from whatever it is that, rather than stimulus information, shall we say. So expectation is the primary thing that we use to make perception. Of course, the expectation is built on previous perceptions, which at some point got grounded in external reality.
But now let me just say though that again, there is, okay, for example, as we've talked about baseball, we know that there's a dorsal visual stream, and we
Yeah.
know that there's a temporal visual stream. So we know that there's neurobiology involved in our ability to predict the path of a moving object.
Right.
So I want to say that there must be neurobiology involved in our ability to predict sounds and fricatives versus plosives. Is that true? That there must
be. Of course, absolutely. There's huge neurobiology in predicting sounds. There's neurobiology in predicting every single stimulus, every single sensory system involves prediction. Probably more than it does in the adult. Probably prediction outweighs stimulus.
I got it right. Because we've learned more about how the world works, and so we are more sanguine in our predictions about. We're more confident in our predictions about the world because our database of past experiences is so much. Because people like me are so old.
Right. I found the book. Okay, I want everyone. This is a really good book. Her name is Stenross, Stenross. I think her first name is Barbara. And the title of the book is Missed Connections, Hard of Hearing in a Hearing World. Hey, and I think I've said that before, but when I read that, I was really nice to my mom for a little while. And then it kind of passed, and I was, difficult with her again.
We're near the end of our little half hour. So, but as you think about the happy ending, the optimistic takeaway from all this, I want to thank all the gang for watching, and thank you for our new folks, Francesca. Thank you, Mike, our beloved Luani, and everybody. We hope and thank all the folks who are watching the replay. Thank the folks who are watching on YouTube.
Can I just make one comment at the end?
I was trying to give you time.
I'm shamelessly promoting, not me, but my mother. She is in the Washington Post today. If you go Washington Post and Jane Mason, you will see a wonderful story about my mother. And I'm just so proud of her. She's so happy. It's a beautiful story for something that she's never gotten enough attention for. And I'm just so, I couldn't be more pleased for her. So go read about my mom. Washington Post, Jane Mason.
Wait, but if they go to, my guess is that if we ask really nicely, if folks go to the Chicago Brain Buddies Facebook page, you would post a link to that story.
Yes, I will post a link to that story. Yes, I will.
And to the book.
Yeah.
Yes. Well, so again, what is your most optimistic takeaway from this brand new research that even you didn't know about?
We're great predictors. and we detect it when we're being fooled.
Yeah.
We're good at detecting being fooled.
But of course, we are never fooled by the sagacious words of one Peggy Mason, the Peggy Mason, the great one, professor of neurobiology, a creator of Understanding the Brain, the Neurobiology of Everyday Life, the wonderful Coursera MOOC that many of us have taken, and the curator and chief and head writer for thebrainissocool.com. And I predict that next week we will be back here, next Thursday.
Yeah, we're going to talk about a really cool new finding from Sam Wang about his, what I think is very interesting, very controversial idea of what's the crux of the problem in autism. Okay. Yeah. And Francesca, yes, that is how you write my mom's name.
All right. Well, you guys should check out the page, the Chicago Brain Buddies on Facebook. You can see the link to the lovely Jane Mason and other things that you will enjoy. Thank you so much, Peggy. We'll talk to you next week.
Excellent. See everybody soon. Bye. Bye.
Well, now I'll tell you, that was just about as much fun as I had here doing this. We're not ending it. It's not ending well. But in the meantime,